Welcome to Weather Basics, Clouds and Precipitation. In this topic, we will look at how clouds and precipitation form, along with their various types. To start, let's look at clouds. First, what are clouds made of? Basically, they are made out of very small water drops we call cloud droplets. These are so small and so light that they can suspend in the air. So when you bring a lot of these cloud droplets together, they form clouds. Clouds form in a variety of ways, but before we touch on those, we need to understand a little bit about the dew point. The dew point is the temperature that if the air was cooled at a constant pressure, saturation would occur. Let's see how this relates to the creation of clouds by looking at a parcel of air represented by the blue box. T stands for temperature, 80 in this case, with the TD representing the dew point indicated by 60 degrees. This happens to equal 50% in relative humidity. Now let's raise this parcel upwards in the atmosphere, cooling the temperature but keeping the moisture, represented by the dew point, constant. The temperature is now equal to the dew point, meaning the air is saturated, and the relative humidity now stands at 100%. In order for the air parcel to cool further, water vapor will have to come out of the air, either in the form of clouds, precipitation, or fog. The air temperature can never be colder than the dew point. Now, let's examine how clouds form. Basically, there are three ways. One is by heating. The sun causes the ground to warm. The warm air rises, cooling as it does, forming clouds. Second is by frontal forcing. Fronts work to push air upward. This upward motion can condense water vapor out of the air, leading to clouds. Third is by orographic means. As air hits an object like a mountain, it can be forced upward. Again, moisture would condense out of the air, leading to cloud formation. Now let's turn our attention to the different types of clouds. Cumulus clouds are fluffy cotton ball in appearance, with flat bases usually developing below 6,500 feet. They form in unstable environments where warm and moist air is rising. Generally, a few cumulus clouds indicate fair weather. However, if the atmosphere is suitably unstable, these cumulus will continue to grow and could become thunderstorm clouds called cumulonimbus. Stratus clouds are uniform in appearance, generally forming a broad blanket of low-hanging gray clouds. They usually develop within a couple hundred feet of the surface and form by lifting a large air mass. Mostly they are precipitation-free but can produce widespread drizzle, light rain, or light snow. Fog is essentially stratus on the ground. Cirrus clouds are the highest of the cloud types, mostly developing above 20,000 feet. Wispy and thin in appearance, they can cover the entire sky. They are composed entirely of ice crystals and point in the direction of the air movement at their elevation. Mostly they occur in fair weather, but can be a precursor to thunderstorms. Exhaust from aircraft high in the atmosphere produce contrails, which is a type of cirrus cloud. While cumulus, stratus, and cirrus are the three main cloud types, there are many variations to these clouds, and clouds are further classified into three different levels: low, middle, and high. Low clouds have bases below 6,500 feet. The major cloud types in this category include stratus, stratocumulus, cumulus, and cumulonimbus. Middle clouds develop their bases between 6,500 and 23,000 feet. The major cloud types in this level include altostratus, altocumulus, and nimbostratus. High clouds generally form above 20,000 feet. The major high cloud types are cirrus, cirrostratus, and cirrocumulus. In meteorology, there are 27 classifications of clouds, with 9 types in each level. Overall, the number of different cloud types exceed 80. Let's take a look at a few of the more interesting cloud types. Mammatus clouds are pouch-like protrusions that form on the underside of storm clouds. They indicate sinking cooler air moving into warmer air. They do not produce severe weather, but can indicate a storm that has or will become severe. Orographic clouds develop in response to the airflow interacting with mountains or other topography. The air becomes saturated as it is forced to rise, condensing into clouds. Most orographic clouds do not produce precipitation, but the orographic effects can enhance ongoing precipitation. ACUS is short for Altocumulus castellanus. These clouds indicate that there is instability aloft and can be a good indicator that thunderstorms will develop in the afternoon. Lastly, Let's investigate precipitation, what causes it, and the varying forms it can take. There are three states that precipitation can take: liquid, freezing, and frozen. Liquid includes rain and drizzle. Freezing includes freezing rain and freezing drizzle. Frozen includes snow, sleet, and hail. There are a couple of ways that precipitation develops. One is collision and coalescence. Essentially, in this process, cloud droplets bump into each other, becoming bigger and heavier, eventually becoming too heavy to stay aloft, so they fall to the ground as precipitation. The other process is the ice crystal process. In this process, both ice crystals and supercooled water exist together in a cloud. Water can exist at sub-freezing temperatures if small enough. Water vapor from supercooled cloud droplets are drawn to the ice crystals, depositing on the ice crystals to form bigger ones. Gradually, these crystals become big and heavy enough to fall, colliding with other ice crystals and cloud droplets on the way down, becoming even larger. Then, depending on the temperature profile in the atmosphere, they can reach the ground as snow, rain, or another precipitation type. The ice crystal process is the dominant process for developing precipitation across the United States. Let's take a look at how the collision-coalescence process works. The blue crystals represent cloud droplets. In this process, cloud droplets run into each other, forming even larger cloud droplets. Eventually, they become too heavy for the cloud to support, and they fall, colliding with other cloud droplets on the way down, becoming even bigger. Eventually, they will reach the ground as precipitation. In the ice crystal process, both supercooled cloud droplets and ice crystals exist together. Water from the cloud drops is attracted to the ice crystals, depositing water vapor on the ice crystals, increasing their size. They become too heavy after a while, falling and colliding with other ice crystals and cloud drops to form even larger ice crystals. These ice crystals will reach the ground now as snow, rain, or another precipitation type, depending on how warm it is at the bottom of the cloud and below it. Let's examine how this can look in a cloud. In this image, we have a typical thunderstorm cloud from the summer. Near the base, temperatures will be above zero. In the middle, 0 to minus 40 degrees. And then usually minus 40 or colder at the very top. Cloud droplets will inhabit the warm region, a mix of water and ice in the 0 to minus 40 region, and then ice above in minus 40. Now let's see how different types of precipitation develop. So here we have a cloud where it is almost entirely all in a liquid form. The cloud drops get big enough to fall as rain. Would this process be collision coalescence or the ice crystal process? If you said collision coalescence, you're right. Now in this cloud, the freezing level is at the bottom of the cloud. Ice crystals fall out of the cloud but melt on their way to the surface, reaching the ground as rain. Would this be collision coalescence or the ice crystal process? You said ice crystal process. You are correct. For snow, we have a cloud where ice crystals fall out of it and it stays cold enough for them to reach the ground as snow. For sleet, it starts out as snow, but as the ice crystals fall, they move through a warm layer in the 1 to 3 degrees Celsius range. This leads to partial melting of the ice crystals, which then refreeze as they fall through the sub-zero layer below this warm region. This results in sleet. Freezing rain is very similar to sleet, falling as ice crystals into a warm layer. However, this warm layer is 3 degrees Celsius or greater, which results in complete melting. Now rain, they fall to the surface where it is below freezing. Thus, the liquid freezes on contact, resulting in freezing rain. Drizzle generally develops on the below-hanging stratus cloud, and it is an all-liquid process. The droplets get big enough and heavy enough to fall, but are much smaller than raindrops and can resemble mist. Freezing drizzle is just like drizzle, except the temperatures at the surface are at freezing or colder. Supercooled water droplets fall to the surface, freezing on contact. Here's a little precipitation trivia for you. Did you know that all the precipitation that falls originated as water vapor from the Earth? Precipitation only covers 2 to 5% of the Earth at any given time. Raindrops fall at speeds of 7 to 18 miles per hour. But do you know how big a typical raindrop is? Is it 1 to 2 millimeters, 5 to 10 millimeters, or 10 to 15 millimeters. For reference, 25 millimeters is close to 1 inch. If you chose 1 to 2 millimeters, you are right. The largest raindrops ever recorded were in Brazil and measured up to 10 millimeters in size. Now, what do you think a typical raindrop looks like as it falls? Is it a teardrop, a sphere, or does it fall in a bean shape? Well, if you chose bean, you are right. A bean, you say? It may not seem like that is possible, so let's see why it happens. Here is a cloud drop, now big and heavy enough to fall to the earth as a raindrop. As it falls, it has to react to the pressure of the air on the bottom of it. This deforms the drop into a bean shape. If the drop gets too big, the drop will break apart into 2 smaller drops, which also take on a bean shape. Let's try some other questions. This type of precipitation forms when it partially melts as it falls and then refreezes before hitting the ground. Is it snow, sleet, or freezing rain? The answer is sleet. Freezing rain is similar, but it develops when frozen precipitation melts completely, then freezes on contact with the ground. What kind of clouds are in this picture? Are they cumulus, stratus, or cirrus? If you said cirrus, you are correct. How about this cloud? It produces thunderstorms. Is it stratus, cumulonimbus, cirrus, or orographic? This is an example of a cumulonimbus cloud. This type of cloud can foreshadow thunderstorm development later in the day. Are they accus, cumulus, cirrus, or stratocumulus? These are accus clouds, which is short for altocumulus castellanus. These clouds point to instability in the atmosphere that can lead to thunderstorm development. Now let's review what we've learned. Clouds develop in 3 different ways: heating, fronts, and orographic effects. There are 3 main cloud types: cumulus, stratus, and cirrus. There are 3 levels that clouds develop at: low, middle, and high. Cumulus clouds are puffy cotton ball in appearance. They develop below 6,500 feet and can become thunderstorms if the atmosphere is unstable enough. Stratus clouds are uniform gray sheets of cloud that usually cover the entire sky. They develop by the lifting of a large air mass and can produce areas of drizzle. Mostly, stratus clouds develop within a few hundred feet of the ground. Fog is just stratus on the ground. Cirrus clouds are high and wispy clouds, generally developing above 20,000 feet. They can cover the entire sky and can be a precursor to thunderstorms. Lastly, precipitation can fall as liquid, freezing, or frozen. Precipitation develops through 2 processes: collision and coalescence, and the ice crystal process. The ice crystal process is the dominant precipitation process across the United States. Temperatures at or near the surface are very important to precipitation type. For further information on any of the topics we have discussed, here is a listing of some good resources.